So I'll start by introducing Raju. So I'm very glad to present Dr. Raju Venugopalan, who is a group leader of the nuclear theory group at Brookhaven National Lab and a fellow of the American Physical Society. He got his PhD in 1992 from Stony Brook University. He had several postdoc positions between 92 and 94 at the University of Minnesota, between 94 and 96 at the National Institute for Nuclear Theory, University of Washington in Seattle. 97, 98, he was a Danish Research Council Fellow at Niels Bohr Institute in Denmark. Then he got his faculty appointment at Brookhaven National Lab. He went through all the stages of the physicist appointments and became a senior scientist in 2007. He is a leader. He is the leader of the Brookhaven Nuclear Theory Group, starting from 2010, with a break for 1 year when he spent his sabbatical, I believe, at the Heidelberg University as an Excellence Initiative guest professor. He has received a number of honors. I will not probably read them all. He is a BNL Science Technology. He received BNL Science Technology Award, Humboldt Prize, and a visiting professorship, Fulbright Senior Scientist Award, and a couple of others. He is serving his community as a co-chair of the program steering committee at Joint BNL Stony Brook Center for Frontiers in Nuclear Science. That's where the seminar will be tomorrow, that he's giving tomorrow. He serves on the AMI Scientific Advisory Committee. In the past, he served as APS Division and Nuclear Physics Executive Committee member and the member of the National Advisory Committee at INT in Seattle. And with that, I think I'll give the microphone to Raju.
Okay, thank you very much for this very kind invitation. I'm especially, and the introduction, I'm especially gratified that you don't have strict time limits because I'm always sort of nervously looking at the clock. That said, please feel free to tell me if you think I'm sort of pattering on a little too much. So it's a real pleasure for me to talk about this topic, which I come to as a novice, even though I've spent a pretty intense year and the last 6 months especially helped by the pandemic, and really trying to think about this problem as deeply as I could. And the title also refers to the title of a paper by Bob Jaffe and Anish Manohar. So this is it's sort of an homage to this beautiful paper. Let's see, which it's the 30th anniversary of the seminal paper. And I found it deeply inspirational. So I've read through really a large part of the literature I've tried to read through on this field, and I keep coming back to this paper because I think I keep learning something from it every single time. I'm sure I've not absorbed all of it. And what's amusing about it is that the title of the paper is Fact and Fantasy on the Spin of the Proton, but I believe it's not what appeared in the journal. So maybe the journal was very conservative in how they wanted their titles to be, as is often the case. Anyway, so this is the inspiration for this paper. And it deals with a problem that we have been thinking about, and this is work in collaboration with my great collaborator, Andrei Tarasov. He and I have been thinking about this problem in the context of the worldline formulation of quantum field theory for some time now. And our paper on this topic will be on the archive tonight. I think I probably messed up the Arizona time again. And two other papers are in preparation, which are sort of part and parcel of this work. So here's my talk outline. I'm going to talk about polarized deep inelastic scattering and the current context. And this is very much motivated by Igor's request that since this is a broad audience, I should introduce them to what's going on and what are the prospects for DIS. And so I'm going to talk about that to some extent. And then I'm going to return to the topic that's dear to my heart, and this is the focus of this talk, which is about polarized deep inelastic scattering. in particular about aspects of it which are sensitive to the topology of the QCD vacuum, as represented by the famous triangle graph, which is sensitive to the anomaly. And then I'm going to discuss very briefly, because I don't have time to do justice to this, this beautiful formalism and quantum field theory, which really enables you to think about the physics of the measure, which is responsible for the anomaly and that of the action, in sort of in kind of an organic way, so to speak. And I'm going to use that to try and discuss a computation where we discuss how we find the anomaly in the box diagram for polarized inelastic scattering. I'm going to talk about how these anomalies dress infrared poles, the Weissenberg-Witten term, and then I'm going to use that to motivate a small x effective action, which builds in the physics of extended PCAC. So I'm going to argue that this is deeply tied to the UA1 problem in QCD, whereby one can actually think of the eta prime as an emergent axion-like field in this effective action. And finally, I'm going to briefly talk about the QCD evolution of this small x effective action, and why one can maybe perhaps think about it also, or some aspects of it in recoupling. And so the latter part of this is still work in progress. And then I'm going to sort of present a conjecture of how spin diffuses from sort of large X of where, you know, the valence partons carry much of the spin to small x. And I'm going to argue that it's a mechanism which is akin to Sphaler transitions. And then I'll end with some general considerations and outlook very briefly. So, so there was a lot of excitement this year. I was at an airport in Mumbai on that day when I got this news that the DOE selected BNL to host a major new nuclear physics facility, and which we will now co-host with Jefferson Lab. This was a very exciting piece of news. This machine, the Electron Ion Collider, will be built over 10 years and it'll cost on the order of $2 billion. And it's going to be sort of the major future facility in nuclear physics research in the decades ahead. In fact, it will be the only collider in the United States for the foreseeable future. Also, I should emphasize that the Secretary of the Department of Energy approved Critical Decision 0, which is approved mission need for those not attuned to these nuances. And so that was approved already in December, and the community is working very hard towards CD1. So there's really a great push to try and realize this as expeditiously as possible. So what's the Electron Ion Collider? So before I get there, I should tell you just a little bit about deep inelastic scattering, wherein I assume you can see my cursor. You have a high energy electron carrying some form momentum k mu, which then scatters of a proton, which carries a form momentum p mu, or a nucleus. And it emits a virtual photon, which carries a form momentum q mu. It's scattered off at some angle theta with an energy e prime, carrying a form momentum k mu prime. And then this virtual photon probes deeply inside the proton. And in the most generic inclusive reaction, breaks up the proton into a variety of fragments. And all you do is you measure the outgoing electron energy and the angle. So for this inclusive process, you can construct the following invariants. So the frame independent, whether you're doing a fixed target or a collider experiment. And these are Q squared, the form momentum transfer squared, which is a measure of the resolution power. There's a measure of the elasticity, which is the energy of the virtual photon divided by the incoming electron energy. And then there's a variable that is x, that's the Bjorkian variable, which is an invariant constructed thus. It's q squared over 2p dot q, which is also an invariant, and which can be rewritten as q squared, the resolution power, divided by the center of mass energy squared times this inelasticity variable, which ranges between 0 and 1. Okay, so for y equal to 1, going to small x is like going to very high energies for fixed q squared. One can also think of this x as a measure of the momentum fraction of the struck quark. So this is in the framework of the parton model. So you can think of this Bjorkian variable, this invariant, as representing the fraction, carried by these partons, so the momentum of the incoming hadron. Okay? So as I said, there's one of the measurements you can do. I mean, this bread and butter measurement is the inclusive DIS measurement with the electron scatters of polarized protons and nuclei, and you measure the scattered electron. And this gives you information on the various structure functions. So the structure functions F2, FL, which sort of encapsulate the physics of these partons inside the protons and nuclei. And then in the case of a polarized target, you can also extract the structure functions G1 and G2, which is sensitive to the spin of the constituents inside the polarized proton. But in addition to these inclusive measurements, you can also do semi-inclusive measurements where you measure, say, an hadron in coincidence with the electron, or exclusive measurements where you just see the electron in some final state and the intact proton. So there's nothing else that's been produced. So it's very, very clean. It's rarer. And you can also do diffractive measurements where you have, say, you have an electron producing some final state, and then there's a gap in phase space between the produced object and the proton, which can then either break up or not. And so these are so-called diffractive structure functions that one extracts, the F2 diffractive or FL diffractive. And so you can do really a whole slew of things, measure nuclear fragments, multi-particle correlations, and so on. So it's really sort of a tremendous range of very clean measurements that one can do because one has exquisite control over the incoming participants in the collision. Now, one of the objectives of deep elastic scattering is really to understand the structure of hadrons and nuclei at very high energies. And one can sort of represent that in a kind of landscape diagram of the strong interactions, where I've plotted on the y-axis this resolution power, q squared, and on the x-axis the parton density, which is 1 over x. This is the Bjorkian variable loosely, or the momentum fraction that I mentioned earlier, that's carried by partons. And so at very high q squared and at moderate values of x, you have a picture of the hadron in terms of quarks and gluons. So that's the great success of the parton model. While at very low q squareds and low energies, of course, one has various descriptions in terms of chiral perturbation theory, the lattice, and so on. So that's kind of the non-perturbative sector of the theory. But then as you go out into high energies, that is smaller x and large, and also stay at a large q squared, then you start probing really multi-parton many-body interactions, which these are sometimes called higher twists. But that's really very interesting. So say if you were to think about the problem as a condensed matter physicist, that's when you're starting to really probe the many-body correlations that start to tell you deeply about the structure of the theory. So, so if you have really a high energy collider where you can access large q squared and high energies at the same time, you're really sort of probing this region here. And then there's a conjecture that if you go to sufficiently small x and you are at sufficiently large q squared, that you reach a regime where the description is in terms of very highly occupied gluons. And these generate an emergent scale, sometimes called a saturation scale. So this is the so-called gluon saturation phenomenon. So in this regime, the coupling is weak because you have an emergent scale, but you have very strong fields as well due to the high occupancy. And so you may really be accessing a regime of the theory where you can use weak coupling to study highly non-perturbative phenomena. And I'll sort of come back to this very briefly at some point in my talk in terms of thinking about this region here. Now, when you are at when you are at low q squareds, where the physics is non-perturbative and you go to high energies, there are effective descriptions of the theory in terms of these non-perturbative objects called pomerons or regions. And it's always been a mystery how to understand these fundamentally in terms of fundamental fields of the theory. And the hope is that that one can use a kind of dual description to this kind of Pomeron-Region fields that one has, and similar phenomena that emerge when you think about this gluon saturation region of the theory, to try and make progress in understanding this region here of the theory. So there are many open questions that one can address in deep plastic scattering, which is associated with this larger picture of the phase diagram, the 3D structure of hadrons, which we still know very little about, spin and orbital dynamics, many body correlations, and small x, like I mentioned. So the Electron Ion Collider, this was the point of the announcement, is going to be built at Brookhaven National Lab. And it's going to be built as part of the RIC complex, where there were heavy ion experiments sort of initiated in the late 90s and will continue until the mid-20s before the Electron Ion Collider, before they shut down for constructing the Electron Ion Collider. And so what you do is you would replace one of the ion rings with an electron ring. So here's where you would inject polarized electrons into the ring. And then similarly, you would use the old workhorse, the AGS, to inject polarized protons and nuclei into the RIC ring. And you'd have a collider experiment then, where the polarized protons can be up to 275 GeV, nuclei up to 0 array of that, and electrons up to 18 GeV or so. So for the electron polarized proton collisions, you would have a square root of S, which can be variable in the range between 20 to 140 GeV. And the design is optimized to reach 10 to the 34 in luminosity. So if this is too much detail, the takeaway is just that this will be the world's first polarized electron polarized proton collider. It'll be the world's first electron nucleus collider. And even though the energies are lower than that of Hera by a factor of 2.5 or so, the luminosities will be about 1,000 times greater. At least that's the projected or desired luminosity for this electron ion collider. So, so the combination of very high luminosities and sufficiently high energies will allow us to really do fine resolution experiments probing inside the proton down to distances of about 10 to the minus 18 meters. So it's, in some sense, this is the ultimate QCD machine in terms of using hard probes to understand the structure of hadrons and nuclei at very high energies. And this has really been a very long and winding road, just to give a sense of how long these projects start. So we organized the first ERIC workshop at Brookhaven in 1999. So that was over 20 years ago. And then the second one was held at Yale shortly after with the help of Vernon Hughes. And here we are. So we had to go through several long-range plans, reports, white papers, and finally received an endorsement from a National Academy of Sciences subpanel in 2018, which gave DOE kind of the the Moody's version. I mean the scientific version of Moody's giving a rating to a company. They gave the approval to the DOE that this science is compelling and definitely should be done. And which led then ultimately to the announcement that I started with. So, so after these preliminaries, let me go to giving you more specializing my discussion to that of polarized deep elastic scattering. And I should emphasize that because the EIC is the world's first polarized electron, polarized proton collider, you're really reaching into terra incognita there. And the objective is to really obtain a many-body picture in spatial and momentum space of the spin of the proton. So we know, of course, that the spin of the proton is 1/2, but it's really a great puzzle, or I would say an interesting problem to understand how this many-body picture that we have of partons resolves itself into the spins of the quarks and gluons and the angular momentum of quarks and gluons. Now, a lot of the interest was provoked or initiated by these, or I would say not initiated, but sort of gained emphasis with fixed target experiments that were done, talking about the decomposition of the spin of the proton into its various constituents. And I was mentioning that the RIC polarized proton collider found evidence for what they call gluon spin, delta G, and that's represented in this plot that's shown here from a global analysis. And the red dot denotes the current value for delta G, but as you can see, which is non-zero, but as you can see, there's large uncertainties as shown in this cross-hatch region. And a lot of that comes from uncertainties in extrapolation of the current measurements to even higher energies or smaller x's. So there's, to really establish that there is non-zero gluon spin as defined here, one needs to really go to do measurements at higher energies to really, or smaller values of x, I should say, to really figure out whether the small value for the spin from the quarks is really compensated by these other contributions that I've listed here, okay, to the spin of the proton.
Raju, while you were absent, there was one question that came up, and it's coming from Jamal. What is the timing of this project for the Electron Proton Collider, Electron Ion Collider? In terms of the energy, will it be kind of all at once, or it will be coming in stages?
Well, okay, so I mean, so I think the plan is to actually start at the highest energies. So we already have proton beams at 275 GeV, and polarization of these protons has been well tested at RIC, but for the electrons, we need to build an electron. We need to build the electron side of this machine. And that is really quite a challenge to build something that would provide very high luminosities and also the energy required energies. But the expectation is that they would want to start at the highest energies. Now, of course, this is the energies of both the electron ring, the electron and proton beams will be variable. So you can sort of study. Do these experiments at different values of central mass energy.
And timing is on the order of 10 years or so, right?
The timing is on the order of 10 years. The idea is to have first collision on the order of 2030. So that's the plan. We'll see how that happens, how that goes, right? So, but anyway, that's the projected plan, and I think DOE has a really very good record of sort of finishing things on either ahead of schedule, or I mean on schedule, or even ahead of schedule. So returning to the problem at hand, in terms of extracting information about the proton spin, a key ingredient is this G1 polarized structure function, and it's directly related to an asymmetry corresponding to the deep elastic scattering, where the polarized proton, as shown here, is polarized either in the direction parallel to that of the virtual photon or anti-parallel. So this difference between the difference between the two cross sections corresponds to an asymmetry, And that asymmetry is proportional to a structure function, G1, which is a function of both the Bjorkane variable that I mentioned, which can loosely be thought of as the parton momentum fraction, and the resolution power q squared. So you measure this asymmetry, so in principle, straightforward. And from that asymmetry, you extract G1. And what we call the quark spin and the proton spin puzzle is the first moment of this distribution. So G1 of x and q squared integrated over all x is this delta sigma, which is the spin of quarks in the proton. Now, of course, to extract this, you need to have this range in x from 0 to 1, right? So the question then is, what are the contributions from the lower values of x? Now, so here's shown the world data on G1 as a function of q squared here on the x-axis for different values of x, as shown here. And you see the world data compared to what's shown here is the projected data we would get from EIC, which was in the Brookhaven case called ERIC. So I've shown, so the world data in this triangle can be compared to what we would have with an EIC. And you see that the coverage in x and q squared will vastly exceed what has been, what exists so far from fixed target experiments. As I mentioned, the EIC will be the first electron polarized proton collider, and all we've had so far are fixed target experiments at lower energy. So we really greatly expand the reach in x and q squared of G1. Now, so it's believed that the logarithmic derivative of G1 is proportional to delta G, and then that would measure the gluon contribution. And so currently there's a tremendous uncertainty on this delta G from DIS experiments, and having measurements in this phase space region as shown here will really reduce these yellow bars, right? Because you'll actually have yellow bands because you have really data there. And so in terms of extracting delta G, that will result in a dramatic reduction of uncertainties with EIC, as shown in this red band here. Okay, so that would really be extremely powerful and interesting in terms of learning something about the spins of quarks and gluons inside the proton. And that's shown in relief here more directly, where I've plotted on the y-axis G1 of x and q squared as a function of now x for a fixed value of this momentum resolution. And you see that the red points here are the EIC pseudo data. So this is telling you how low in x you can go. And you can go to x values, which are about 1,000th, where partons carry about 1,000th the momentum of the proton. Okay, so these are very soft partons inside the proton. And so at the highest DIC energies as shown here, which is 141.4 GeV, you can kind of, that's what the blue dashed lines indicate, the extended reach that one would have. And as I mentioned, you can vary the energy. So you can sort of get data on this entire region as well. And so that's going to restrict, so it's going to really add a lot of clarity to our understanding the lower limit of this integral here, thereby allowing for more precision extraction of this delta sigma, which is the quark spin in the hadron. So much so that, as shown in this plot here, where the big blue blob represents the current uncertainties in delta sigma, the integral of delta sigma and the integral of delta G, so that's the gluon spin and this is the quark spin. And you see that the combined uncertainties are huge, right? But now with this precision data from EIC, that's going to shrink to this tiny little blob here. Okay? And so we can really learn something really new in terms of these experiments and constraining these objects as shown here. So that would be very exciting in terms of precision. So now let's come to the actual subject of my interest and contribution towards this problem, and that's related to something that sounds kind of obscure but is really extremely important, and that's the isosinglet axial vector current. and its relation to the topology of the QCD vacuum. So if you want to look at some reviews which are related to what I'm saying, these are given here. So let me start. Since it's a theory colloquium, I have to give some definitions. So what I'm going to be talking about is related to the hadron tensor, which is the imaginary part of the time-ordered product of two electromagnetic currents inside the polarized proton. So imagine that you have a proton here that's polarized, and then you have the quarks and gluons there, and then you stick in a current, electromagnetic current here, represented by the virtual photon, and another current here. Okay, and taking the imaginary part, you're taking this red dotted line here of this Feynman diagram. And so that tells you what W mu nu is. So you're really computing the autocorrelation of two electromagnetic currents at two different space-time points. So this is a real-time correlation. And its Fourier transform is really what's giving you W mu nu. Again, the current is defined thus here, and J mu summed over all flavors of this current for each different quark. Now G1 can be written simply in terms of this. It's a projection of this the anti-symmetric part of W mu nu. W mu nu has a symmetric and an anti-symmetric part. G1 can be thought of as a projection of this anti-symmetric part, where S mu for a longitudinally polarized proton is proportional to, can be written as something proportional to P mu, where P mu is a four momentum, and lambda of 1 plus minus 1/2 is the helicity of a quark inside the proton. Now, in the parton model, to leading twist accuracy, you can write G1 in terms of the sum of the helicity quark and anti-quark distributions as a function of x and q squared. And formally, this helicity parton distribution function, sometimes called PDF, can be written in terms of this current here, psi bar, at some position y minus. This is the light cone distance y minus, and then the gamma matrices gamma plus, gamma 5, psi naught, again sandwiched inside the proton. Simply put, what delta x tells you is the net helicity, where you have quarks pointing in the direction of the proton or anti in the direction of the proton. And delta QX is a measure of that very important quantity. Okay. Now, the first moment of G1 in general, because I also have a sum over the different electric charges of the different flavors, you can decompose it into this kind of structure here, where these three F plus D correspond to some combination of the...
There were one or two questions here. It's closely related to what you were talking about. So Giorgio, you want to go with your first question?
Maybe it was for the end. I was just wondering if one can probe the gluon spin directly via vector meson production or something like that. The gluon spin part of the distribution function.
Yeah, I mean, so people certainly, yes. So people, for example, talk in terms of producing, so if you produce, say, a charm pair in polarized DIS, then it's sensitive to, features of the gluon spin. Certainly. And there's quite a bit of literature on that, which I'm not the world's biggest expert on, but certainly there's quite a bit of work on it.
And Henry, you had a question you might want to ask.
Yes, again, I was wondering about the neutron. What can we learn from the neutron and apply to the proton and vice versa, whether it be theoretical or experimental? I mean, what are the relationships in that?
Right, so for example, I mean, the Bjorken sum rule, for example, also, which really provides you very high precision data on alpha S, for example, and is a great way to test BSM physics. Also is also given is in terms of the difference between the G1s for the proton and the neutron.
Thank you.
I think that's all we've got.
Yeah. And also people have done measurements using polarized neutrons. Yeah. Where was I? Okay, so as I was mentioning, that what is of interest to us though is this isosinglet quark helicity, which as I mentioned is related to the spin of a proton. And that's defined as the sum of delta Q and delta Q bar for the light quark. So it's summing over all the light quark flavors, and that's what gives us delta sigma. So it's a isoscalar flavor singlet. Now in the parton model, this mixes under evolution with the other isospin blind moment, which is delta G, which that's the integral of delta G of X from 0 to 1. Okay, so it's the first moment of the gluon spin. And in principle, you can write down something like a renormalization group equation, an Altarelli-Parisi type equation, where you can study the evolution of these two isospin blind polarized parton distributions, delta sigma, that of the quark spin, and delta G of the gluon spin, in terms of this, in terms of each other, which is proportional to this matrix of splitting functions that describe the probability of polarized quarks going to other softer polarized quarks or gluons going to quarks or gluons. And so these are called splitting functions. They're Mellon transforms of anomalous dimensions of operators that represent these quantities. And they've been computed to very high loop order now. So there have been 3 loop computations, which have been done by the folks listed here. So in that sense, this is a very highly developed aspect of perturbative QCD. Now, the interesting and novel thing for the general audience in terms of this isosinglet axial vector current is that it's really the matrix element of J mu 5, the isosinglet axial vector current. And we know from the chiral anomaly in QCD that d mu J mu 5 is not 0. So this current that we are saying is coupled to the proton is not a conserved current. Okay? In fact, you can write this d mu J mu 5 in the form that's listed in this box here. And where K mu is the Chern-Simons current, okay? That has to do with the winding number of gauge field configurations in the QCD vacuum as illustrated here. Okay, so in that sense, and in fact, d mu K mu is the product F times its the field strength tensor F mu nu and its dual F mu nu. So it's E dot B, okay? So that's a topological object. And then there's a mass term, which in the case of massless quarks, you can put equal to 0 or it's close to 0. So really, d mu J mu 5 is related to FF dual, which is again deeply connected to the topology of the QCD vacuum. Now, because I have this relation here from the violation of the anomaly, that is d mu J mu 5 is equal to 2NF times d mu K mu, I can bring the first term on the right-hand side to the left-hand side, and then that current, which is J mu 5 minus 2NF K mu, would be conserved. And then it was argued, starting from the late 80s, that in a certain gauge and frame, this K mu can be interpreted as the gluon helicity, okay, delta G. So you could take this expression that I have for K mu in terms of gauge fields, and then in a particular gauge frame, you could write that in terms of the gluon helicity. And so then the argument that followed was that the real spin of the proton, the one that's conserved, right, for which d mu J mu is 0, is really given by the non-conserved spin, that is the sigma tilde minus the gluon spin. So if the gluon spin were large, that would explain why the spin of the quarks in the proton is unnaturally small. Okay? And so this was kind of seemed like a very attractive explanation, and that actually motivated a lot of the experiments to actually go and try and compute delta G and see if it's really large, as I mentioned. And I showed you the plot, which shows the current uncertainties in determining this. Now, this seemed like kind of a very attractive thing. However, as pointed out by Bob Jaffe and Anish Manohar, the identification of this Chern-Simons charge with delta G is intrinsically ambiguous. And the reason is that this delta G is gauge invariant, while K mu, the Chern-Simons current itself, is not gauge invariant. Okay? And that it's as shown here, it's not invariant under large gauge transformations, which are really a deep consequence of topology. So while you can mess with a lot of things and ignore things that have to do with boundary conditions and infinity, when it comes to topology, they are of the essence. And so they shouldn't be confused with each other. And in fact, as Bob Jaffe's emphasized, the identification of K mu with delta G has been a source of much confusion in the literature. And he has a set of very nice lectures where he has discussed this in some detail, some of the issues with this identification. So, however, say you do that, right? And then you find that this evolution equation that I alluded to can be written in such a form that you see that this was actually first due to Altarelli and Lampe, who sort of argued this already at leading order in the evolution. But they, you see that even when you do these very difficult three-loop computations, the splitting functions that you get can be expressed in the way that's shown here, whereby delta sigma only mixes with itself, while delta G could also mix, well, delta G also mixes with delta sigma, but there's only one splitting function that controls the entire evolution, okay? And so this is really very nice to see that up to this three-loop order in computations that this is really satisfied, and this was emphasized by De Florian and Vogelsang recently, okay? So what we are going to argue is that there's a real deeper physics behind these expressions, and it's really manifestation of a symmetry that should hold to all orders. And that's related to the topology of the QCD vacuum. Now, there's another alternative picture, which I feel hasn't gotten as much attention as it deserves. And this is related to the general set of considerations having to do with what's called the UA1 problem in QCD. And this goes back to the work of Veneziano and his collaborators. And essentially, it has to do with the physics of the eta prime in QCD. Okay? So as shown here, I've shown you here, these blobs here represent, all possible diagrams that contribute to the effective action, in where the black blobs denote sources that one can have in the effective action. So this is, say, the Zumino effective action that people write down. And you see that, so naively, there are so-called OZI allowed contributions, which are not NC suppressed, but then they are OZI suppressed contribution having to do with gluon exchanges, which are. Now, as was pointed out by Witten and also with Veneziano, that these 1 over NC corrections are very important in understanding the mass of the eta prime. Okay? They're fundamental to understanding the mass of the eta prime. And the Witten-Veneziano formula, where the mass of the eta prime is given in terms of the topological susceptibility, that's this Chi-Yang-Mills, or Yang-Mills, a pure Yang-Mills theory, and the pion decay constant is an example of this, okay? Where the topological susceptibility as a function of forward momentum squared p squared can be written as the autocorrelation function of the topological charge density at two space-time points, okay? And so as they argued that this sigma here can then be written in terms of a coupling of this topological charge density to the form factor where this topological charge couples to the nucleon, plus a term of where you have eta prime coupling to the nucleon times the square root of the slope of the topological susceptibility at p equal to 0. Now in QCD, in the chiral limit, this chi of 0 for full theory, not just Yang-Mills, is 0. It goes to 0 for massless quarks, while the slope is non-zero, but it's small. So you can use some rules. I'll discuss that a little bit. Tells you that you have a small value, and principle also explains this sigma. So this is a radically different picture from the one that I articulated in the previous slide. Okay? And so what is the underlying dynamics? Can we reconcile this picture with the perturbative one? So these are all kind of interesting questions that one can come to. But central to all of this is the behavior of the triangle graph, the anomaly. So remember that the isosinglet axial vector current, the matrix element of that is what you see in the parton models you see in the expressions I showed you is proportional to delta sigma, and that involves this coupling to the anomaly. Okay, so that's this triangle graph here shown with these three momenta, where the off-forward matrix element for JMU5, where P prime, so the incoming and outgoing proton have slightly different momenta, with the moment that's given by L mu. Okay, so it's L mu going to 0. So you take a limit where T is the Mandelstam T variable, that's L squared. And so you can think of really this delta sigma as the forward limit of this off-forward matrix element. And in general, that can be decomposed into two pieces. One, which is an axial, so it's an axial singlet, isosinglet form factor. And then you can also write that, and plus a term, which is the pseudoscalar form factor, okay, for the isosinglet. And so this is a general decomposition that one can write down, and this was shown by Jaffe and Manohar in their seminal paper. Now, when you try to compute this object on the right-hand side, as opposed to just write down this general decomposition, when you compute G sub A, that's the triangle graph. And when you compute it, you find that it has an infrared pole. Okay, and that pole is proportional to L mu or L squared F of dual. So in the limit that L squared goes to 0, it diverges. Okay, so it's not a logarithmic singularity, it's an actual pole. So what you can show that when you actually compute things, right, this axial form factor has a term which is singular, okay, which is L dot S L mu or L squared times the kappa of T. So that's the F of dual piece. Plus then two terms. So the statement was that you could decompose the second term also into two pieces. And that has likewise an identical pole, but with the opposite sign, okay? And so for the two poles to cancel, as they must to give a physical result, lambda of 0 must equal kappa of 0, okay? And then you cancel the pole. And the final answer is nicely S mu of lambda of 0, which is in turn proportional to F of dual. Okay? This physics, this cancellation is precisely what is a consequence of the Wesu-Minowitten term for the eta prime. Okay? And in fact, it's widely employed in low energy effective actions to describe the eta prime in chiral perturbation theory, which is really compared to a lot of low energy data having to do with eta prime. Okay? So this is really a very important fundamental way in which the pole of the anomaly is canceled to give a final result. It comes from a non-trivial decomposition of this tensorial structure that's shown here. Okay? So this is what I learned from this very beautiful paper that I alluded to several times. So the final result that one gets is for sigma, as a consequence of this cancellation, is something which, again, one has to think about carefully in terms of taking the limit L mu going to 0, is the trace of F of dual times 1 over L dot S, okay? This 1 over L dot S is very important because if I just take the matrix element of f of dual in the forward limit, I would get 0. Okay? So the fact that L dot L is going to 0 and f of dual is going to 0 is what gives you a finite result in the day. Okay? Now, to my great surprise, and I've looked at a lot of the PQC literature, as I said, being holed up during the pandemic and even earlier, surprisingly, even though this is well known to Jaffe and Manohar and to Venugopalan and collaborators and a large community outside this field, it's not addressed in a lot of the PQC literature. Okay? And it's a deeply profound point because this is intimately connected to the mechanism whereby the eta prime gets its mass in QCD.
Raju,
So the takeaway message
Raju?
is that this result and its generalization to G1. Okay.
Raju, there is a question.
Yeah.
Yeah,
Go ahead.
Raju, I just want to make a comment that you probably missed the lattice QCD literature. Cafe Liu and his company have spent last 15 years or more try to calculate the sigma using exactly this anomaly equation on lattice.
So how do they compute the pole?
They try to calculate the sigma from the anomaly term. They calculate it. Yeah.
Yeah. So if I can just say it, so I've looked at actually quite a bit of the lattice literature, including the paper that you sent me. So I'm not sure. I can't remember.
Okay,
but,
I can send you the reference.
But the point and I'll come to this in greater length later. And I think we should discuss this at length. So let me come back to this point. Okay, so I will, if you don't mind waiting a little longer, I'll come back to this issue of the lattice computation.
Okay.
Okay, so I mean, it's a deeply interesting and important point, and so I think it deserves a more extensive discussion, and I hope we'll have time to discuss this. So if I may, I will.
Yeah, please continue now.
Okay, so yeah. So let me now come to the specific computation that I'm talking about, which is in terms of thinking properly about anomalies with worldlines. And so there are some reviews I've cited here in some of my work also where we addressed this recently. And I want to emphasize that this is not something terribly exotic, okay? I hope that's not the takeaway message. The worldline formulation of quantum field theory is exactly equivalent to the string amplitude formulas of Byrne and Kosover, which has been used to compute, in perturbative QCD with great efficiency, very difficult computations, and is really also being pursued in the string community. And the equivalence of that forms into the one that I'm talking about was shown by Strassler almost 20 years ago. Okay, so this is not something that is an exotic off branch that I'm talking about. So in the worldline formalism, you can write down the action in QCD in terms of vector and axial vector fields, where you can think of these axial vector fields as auxiliary fields in the QCD Lagrangian. And so then from this, you can compute the one loop effective action. And that can be written as a log determinant of this Dirac determinant, which is d slash plus a slash plus gamma phi a5. Okay, so where that's the auxiliary field. Now there's a beautiful heat kernel representation of this gamma inside of this Dirac operator, where what you do is you sandwich that between 0 plus 1 dimensional boson, which is X and P, and fermion, which are point particle Grassmannian coherent states. And that was described in some of the early string literature, but also in this very beautiful paper with Berezin and Marnov in Annals of Physics in 1976. And so essentially, you can think about these gamma matrices as being the operators to generate coherent states with creation and relation operators defined thus. That's this Wigner-Weil formalism. And you can write down their eigenvalues in terms of Majorana fermions. So these are real objects here, the psi i's, and that will be the objects that I'll be studying. And so the nice thing about this formalism is that you can treat, so when we compute path integrals in QCD, so there's of course the physics coming from the action, but the physics of anomalies is deeply tied to the measure of the path integral, to the phase of the determinant. Okay? And as as was shown to us by Fujikawa so a long time ago. Okay, now it turns out that you can also rewrite this in terms of an imaginary part of this effective action, where that's the phase of the determinant. Okay, and so this is a very elegant way to represent the chiral anomaly, which comes from the, as I mentioned, from the non-invariance of the measure under chiral rotation. So remarkably, as shown in a really beautiful paper by De Hocker and Gagne, this phase can be written as a form of an action which is nearly identical to this real part. Okay? There's a slight difference which is important, but for most cases not relevant. But one could just think of it as a useful mnemonic that the odd powers of gamma 5 in any computation in the argument of the path integral contribute to this imaginary part, and even powers to the real part of the effective action. So going ahead, one can use this to compute the triangle anomaly, okay, in the worldline formalism. Now, and so it's in, so if any of you have actually looked at the actual computations by Adler, Bell, and Jakiv, it's highly non-trivial how one computes the triangle anomaly in perturbation theory. Okay, if you don't do it carefully, you'll get linearly divergent results. Okay, and so you have to impose ward identities very carefully on the general tensorial structure of the triangle graph to obtain the correct result, as shown by these gentlemen here for QED, and then generalized later by Bill Bardeen to non-abelian gauge fields. However, in the worldline formalism, it comes out, almost, I wouldn't say trivially, but straightforwardly. Okay, so all of these objects that they talk about in terms of imposing all these ward identities, this chiral ward, are manifest in this form of the effective action. And so you can just compute this, the matrix element of interest that I said here, the isosinglet axial vector current, in terms of the functional derivative of this gamma here with respect to A5, and then you set A5 equal to 0. Okay? And what you get, lo and behold, is the anomaly, okay, which is the trace of FF dual. But very importantly, this has an infrared pole. Okay, it's L mu over L squared. Now, somehow in a lot of the literature, this L mu over L squared is not taken into account. So this is a deep problem because when L goes to 0, this diverges. Okay, so what is often done in some of the papers in the literature is that this pole is just replaced by S mu or SK in this S kappa in this context, and then the rest is what is interpreted as the anomaly. Okay, so they say the anomaly is finite, and that's the coefficient of the anomaly. However, in doing so, they've essentially made an assumption about a particular assumption about the regularization of this infrared pole, which, as I said, is deeply tied to the eta prime problem in QCD. Okay. So when people say, oh, we have the anomaly, well, I look at the paper and there's no L mu or L squared there at all. Okay, so I don't really understand what is being said then in that context, because this has an infrared divergence that has to be there. And this is a well-known result going back to the late 60s in QED and in the 70s for QCD. Okay? So let me now come to the computation of polarized DIS in the worldline formalism. And so you can really think about this problem as computing the polarization tensor, the anti-symmetric part of the polarization tensor in a gauge background field. Okay? In this case, corresponding gauge fields corresponding to gluons. So, and that corresponds in QCD to the box diagram for polarized deep inelastic scattering. Okay? And so one can compute this box diagram. So the polarization tensor, and this is an exact representation, there's no assumptions in what I've written down here, can be written as a box diagram which corresponds to the four gauge field external lines. So mu nu from the photons with momenta K1 and K3, and alpha beta from the gauge fields, which interact along the worldline trajectories at 4 different proper time points, tau 1, tau 2, tau 3, and tau 4. Tau 1 and tau 3 being that for the photons, and tau 2 and tau 4 being for the gauge fields. Okay? So now this box diagram can be computed. So the general expression for the box diagram is quite complex. However, in the Bjorken limit of QCD, which corresponds to very large Q squared, so it's an asymptotics of QCD, where you formally take Q squared to infinity and the central mass energy squared to infinity while you keep X fixed. And in the radial limit, which is the other opposite limit in deep inelastic scattering, where you take X going to 0, so the parton momentum fractions, or the Bjorken variable specifically, goes to 0 with S going to infinity while you keep Q squared fixed. Okay?
Sorry, Raju,
So,
what gauge do you work in?
So at this point, we have really not worked fixed a gauge at this point. So we're just computing this in the general background field. Okay, so our result you will see is gauge invariant. Okay, so all we are using in this computation is we are using the water identities that are satisfied by the gauge fields, and we will use the fact that the background fields in the Bjorken limit have 4 momentum squared either equal to or close to 0. Okay? So it's on the order of lambda squared QCD. Okay, so that's the only assumption that's being made in this computation. Okay, and the result that we get is a gauge invariant result, as I'll discuss now. So and I'm going to emphasize that these results, especially in the radial limit, are completely new. Okay, so no one's ever written down an expression for G1 in the radial limit, and the Bjorken limit. People use the OPE, but and I'm saying we do not use OPE in our computation. It's a direct computation of the box diagram. So this is an exact representation of W mu nu, where you have the correlative currents, and you write this in terms of polarization tensor, and that's the box diagram. So what's amazing is that the result is identical in the 2 limits. Okay, so that was really remarkable. However, if you think in terms of a visual representation of the word lines, it seems almost, it seems almost matter of fact in a way, because what the Bjorken limit corresponds to is where you pinch together the 2 proper times of these virtual photons, which are K1 and K3. So that's Q squared going to infinity. And so the photon probe is really a point. And so this K1 and K3 get pinched together to a point, and then you get a triangle. Okay, so, and where K2 and K4 are the gluons. That's a Bjorken limit. Now the radial limit is the opposite limit, where what you're doing is you're pinching together tau 2 and tau 4. So essentially, the gluon background field is a shock wave of infinitesimal thinness. And so essentially, you have an inverted triangle. Okay? And so these are the leading contributions. So we have done an explicit computation of the full box diagram in both limits. And what we find is that for G1 in the Bjorken limit, which is Q squared going to infinity, is the following result here as shown. That's the first slide. And then has this infrared pole, okay, L mu over L squared times this non-local FF dual, plus non-pole contributions, which are suppressed by lambda squared over Q squared, which go to 0 as Q squared go to infinity. The radial limit result, that's a typo that I made there. I actually cut and pasted the same formula, but it should be really XBJ going to 0. Has exactly the same structure, but the corrections to the box diagram are QS squared. So it's a typical KT of the background gluons, which I will call QS, and divided by the invariant mass squared, which is proportional to the energy. Okay, so even for small momentum fractions, that energy in the radial limit goes to infinity. And so these corrections are very small. Okay, so what we are arguing is from explicit computation of the box diagram, okay, imposing all the water entities, where we recover exactly the ABJ result, in the same formula, in the same formalism, we recover the results, these results for G1 in both the Bjorken and radial limits, okay? Now, what's amazing is that when you compute the full box diagram in the Dworkin limit, the formal expression of the computation has explicitly the triangle graph times some finite pieces, which are just sort of irrelevant prefactors. Okay, so already there you see that it's completely controlled by the topology. The explicit computation of both gives you exactly this anomaly pole, and that's true even in the radial limit. So what we are concluding from this computation is that G1 is entirely topological in both asymptotic limits of QCD. And if something is really tied to really the detailed structure of the vacuum, that is what one would expect, actually, that is the case, right? That independent of the kinematics of the problem of the probe, if it's really a property of the vacuum that's being probed, then this is what you would expect. So from this perspective, its relation to delta G of X and Q squared is unclear, is what I would conclude, okay? As I said, in a lot of the literature that I've perused, this L mu or L squared pole is ignored, and what people call the anomaly is just the rest, okay? But this is infrared divergent, and in fact, just the trace of this F dual, when you take the 2 points together, would just give you 0. So it has to be thought of as something that goes hand in hand with this object here. So how is this cured to give a finite result, right? So, and as I said, pseudoscalar fields play a very important role in this problem, just as in resolving the UA1 problem. So when I wrote down the previous expression for the worldline path integral, I did not write down the most general form of the imaginary part of the effective action. And that's, you can find in this nice paper by De Hocker and Gagne. And that has a form which includes the structure, which is du pi, that's the derivative of the isosinglet, it's a derivative, sorry, of a pseudoscalar field, times the psi mu psi phi, which is very similar to the expression that one has for the spin precession term, okay? And you also have a term where you have something proportional to the chiral condensate, which also turns out to be important. Now, if you expand out this worldline Lagrangian, you will find explicitly that the first non-trivial contribution to this WI is the Wess-Zumino-Witten term. And as I mentioned to you, it's a Wess-Zumino-Witten term that you can write down in terms of F dual, which exactly cancels this infrared pole of the anomaly, okay? So let me pose to you the following point, that suppose you were to regulate this infrared pole without taking into account this pseudoscalar divergence from the Wess-Zumino-Witten term, then in QCD, you would have an infrared pole that's left dangling, okay? So in order not to have that infrared pole dangling, this particular mechanism of cancellation is essential to get you, sort of sensible results in the full theory in QCD. And this Wess-Zumino-Witten term, as I mentioned, in the chiral perturbation theory literature is extremely well known, okay? In fact, there are very high order computations in that framework which take into account precisely this eta prime to F dual coupling, okay? And as I mentioned, this exactly cancels this perturbative computation to the anomaly. So our claim is that at the end of the day, if you include this physics, what G1 goes to would be the following structure where you're taking the bracket of P prime and P. So remember, P prime is the outgoing momentum of where things are off forward. So L is the off forward for momentum, where you sandwich in the argument the topological charge density and L, okay, in the denominator. Now, if you just had the topological charge density, when you take the forward limit, you would get something 0. So you need to have this L in there. And it's the computation of this matrix element, which is going to be the subject of our upcoming work, and for which I will just sketch out the outline of how that goes, okay? So when you compute this matrix element, one can do this as taking the trace of the operator times the density matrix. Now this density matrix for quarks, which you say start at -infinity, so you have 3 valence quarks at -infinity, you turn on interactions. That's given again by the worldline effective action. That also contains in the density matrix a psi 5, which is like gamma 5. So that projects out the measure, okay? And one can do a careful calculation, okay? So you have to take a smear out shock waves and so on. But the key effect is again this gamma 5, which induces zero mode, okay? So basically what it does, it takes anti-periodic boundary conditions of fermions and converts them to periodic boundary conditions in this path integral. And that is the origin of the coupling to the topological charge, okay? And so there's a very nice this paper I came across by Ben Bakker, Elliot Leader, and Larry Truman, who also argued about how one should carefully treat all forward matrix elements that you are welcome to also look at. So what you find when you do this, can you compute this density matrix, is again, what only survives is FF dual, okay? So essentially, this gamma 5 changes anti-periodic boundary conditions to periodic boundary conditions for the Majorana modes. And the anomaly term arises from the surviving zero mode. And so the final result you get is some combination of this, of the theta term, that an emergent theta term that one has in this computation, and the eta prime pseudoscalar term, okay? So this is the primordial eta prime, the eta naught, which is massless. And it's this combination of the two which gives a mass to the eta prime, okay? So, and what that does is that it looks like an axion-like effective action in many ways, okay? And so that's what I'm going to come to. But let me just mention that the final result of Veneziano and collaborators by Narison, Shor, and Veneziano is that the form for delta sigma is not just, I mean, you cannot just write that as, you know, expectation value of F of dual, that would just be 0. But actually, it's this non-local object, right, as shown here in these two figures here, which corresponds to an autocorrelation function between the topological charge at 2 points. One is in the box, and the other is inside the proton, and the other such contribution will be from the topological charge and the eta prime. Okay, so you have two such vacuum matrix elements, and as I mentioned previously, the first one is 0 in QCD and the chiral limit, while it's a second term, which is the chi prime, the derivative of the topological charge density, that should be measured. So from this logic, what one should measure on the lattice is the derivative of the topological susceptibility on the lattice, p squared equal to 0. And this was actually done using some rules, okay, not on the lattice, but it was done by using some rules by Narison, Shor, and Veneziano. They had these papers. And they claim that their results are in agreement with the Hermes and Compass data, okay, at least consistent with that. So I'm personally agnostic about that, but okay, I just want to point out that there's a model computation in their framework, which actually they claim is consistent with this topological screening picture of the QCD vacuum. Now, what I'm interested though is in small x, where the lattice is the least accessible. And there, it turns out that one can bring in a new set of tools and techniques to bear, having to do with these large gluon occupancies that one has. So if you think about a Gedanken kind of situation, which is appropriate in the radial limits, imagine you have, say, long wavelength gluons, which are coupled to a lot of spins and color, you know, which carry also color, right? So in this worldline picture, you have an ensemble of spinning colored partons at some given x. And then you can write down for G1 the appropriate path integral, and taking into account the physics of U1, you can kind of guess what the structure of this effective action is in terms of the topological charge density. So I've cheated a little bit and I've changed notation on you. Here, omega is the topological charge density, not Q. So I've used them interchangeably, and I apologize for that. But then there's also this term where you couple the topological charge to this eta field, which I call psi here, and then there's a kinetic term. Okay, so this form of the effective action was already posited by Veneziano and actually goes back to some of his original seminal work on the UA1 problem. So this term can be rewritten in several ways. And in the form that's shown here in terms of this blue ball kind of effective action is the essence of a chiral perturbation theory formulation for the pseudoscalar non-net, as you can see in this paper that I referred to here. And you get the Witten-Veneziano formula and so on. Equivalently, you can write this effective action in a form that I will find attractive to use in terms of a psi plus theta times omega. So theta is a QCD theta term, and then you have a term proportional to the topological susceptibility, which is chi of Yang-Mills. Okay, and this psi plus theta squared term is extremely important, and that's the reason why we call it as being axion-like, because in case of the axion, you get this kind of structure for the potential. Now, this theta is something that you can get rid of with the shift symmetry, and so in the end, it's really all due to the dynamics of the psi field. So in my final section, I'm going to conjecture how things may look like when you go to small x. And before I do that, I should mention that there's a lot of very impressive work on perturbative computations of G1 and small x as listed here. And the question is, can we reconcile all of this nice work with the dynamics of the chiral anomaly at small x? Now, in some sense, the answer is yes, because what you're doing when you're computing the triangle in the, or this G1, in the small x limit is you're really smearing out the shock wave, and all the evolution is taking place inside the shock wave. And so what one is really doing then is renormalizing this axion effective action systematically at small x in the same way that people do for the unpolarized case. And what one then would find is a fascinating interplay between gluon saturation, which is controlled by the saturation scale QS, which allows you to treat the problem of recoupling, and spin diffusion, which is controlled by the topological charge density, which is this omega that I had here. And this is something that actually has been looked at in the past. So people have thought about this in the context of a hot plasma. So there's a nice paper by McLaren, Mottola, and Shaposhnikov where they thought in terms of the diffusion of topological charge at finite temperature. And I and my collaborators have also looked at this in the context of overoccupied gluons out of equilibrium, okay, also real time. And we find this result that's shown here is that you find that you can actually compute the autocorrelation of the Chern-Simons number, which is the Fowler-Rome transition rate, as a function of the Chern-Simons number difference. And we find that when we do this on a lattice for overoccupied fields, we can cool things on the lattice. And what you see are integer valued configurations as represented by these histograms sticking out of the left plot. Okay, where you see that things really line up at integer values of this Chern-Simons number. And so you can count those and estimate what the Fowler-Rome transition rate is. And you find that it scales with the string tension that appears in the Wilson loop, okay, in the spatial Wilson loop. So the analogy of time here in this context is the rapidity. And so the argument would be then the diffusion to small x is controlled by the rate of Fowler transitions, where the scale, as I mentioned, appeared in the topological susceptibility that I mentioned here. So just very crudely, but perhaps usefully, one can think about spin diffusion of Fowler transitions as being a sort of diffusion of quark spin in disordered, topologically disordered media, where the vacuum can be thought of as lumps which carry, which are spatially localized in color charge. That's this QS scale, but they also carry topological charge. Okay, and so as we know from the index theorem, that the helicity flip of massless quarks is given by the difference between left and right-handed quarks being proportional to the total topological charge of each of these blobs. Okay, so essentially you have a random walk, these quarks, that go through these blobs and then that flip their helicity, okay? And as you go to smaller x, what you'll find is more and more of these blobs, okay? So the chances that you would lose more and more helicity gets greater and greater, so you're essentially having damping of spin. And so that's really what's going to damp out these things, giving you the full helicity flip. need to see to really compute the spin, the helicity of the proton. So to summarize, I apologize for all the technical glitches and difficulties. And I hope this is still, some of you have stayed doggedly through the end. But I want to mention that all of these ideas can be tested at an electron ion collider. In particular, many of these issues are deeply connected to each other. You know, what is the nature and origin of the nucleon mass in terms of its various components? That's related to the conformal anomaly. The origin of nucleon spin is related to the chiral anomaly. And then gluon saturation can also be explored, and we have an effective field theory to study that. And likewise, nucleon tomography can be studied using effective field theory and the lattice. Okay, so so we have in the IC the possibility of using precision probes to study the strong interplay between perturbative many-body dynamics of partons and the non-perturbative structure, the ether, so to speak, of the QCD vacuum. So thank you very much for your patience.
Thank you for the presentation. We now have some time for questions. If anybody has a question, Giorgio, you are the first. Go ahead.
Oh. Raju, thanks for a really thought-provoking talk. I'll be digesting it. It's tonight that the paper will be on archive, right?
Yes, yes.
Just as a, we all know that for reasons we do not know, theta equals 0. I mean, the asymptotic part, the FF, right. The expectation value of FF tilde is 0, and this is related to your pole cancellation in the middle of the talk. And right. This is sort of an infrared effect. This doesn't have to do with the peak of the instanton. This has to do with the asymptotic topological behavior of space-time. Right. Here, you have, you know, instead of a topological space-time, in the saturation picture, in a sense, what you're expanding around is X going to as far as possible, right? I mean, you see things at mid-rapidity, and X really, I mean, if you consider the whole event, X goes from very close to 1 to as close to 0 as we can possibly get, right?
Right, so these are very slow partons inside the hadron, yes.
Do you think that there might be sort of interesting transitions? I mean, I'm trying to phrase it. So here you have, if you consider the whole accessible X range, you recover theta equals to 0. You recover theta equals to 0. But if you're observing only a certain part, you have topological susceptibility, you have fluctuations, and the transfer between spin and angular momentum is something similar to this. Do you think something non-trivial will happen in the sense that as you go from, for example, a small rapidity range into a wide rapidity range, and you consider the evolution of the parton distribution functions, you will have topological transitions or something like that? I don't know if that makes sense.
Yeah, I mean, so in some sense, that's precisely what I'm saying is that, and that's the essence of the two pictures that I showed you, is that, I mean, as you go from, I don't know if I'm not able to change my, so as you go from, say, one rapidity to the other, you see that the lumps as viewed by the probe get smaller, right? And they get many more of them. And so all of these carry topological charge. So at least, you know, as viewed by probe, you're going to see very different structure, you know, that's representing the vacuum.
Mm-hmm.
And this is really what is causing, you know, spin diffusion, right? As you go to small x. So one can study from measuring, say, the slope of G1, you know, in principle, if this picture holds, then you're really learning about this process. And then you can also try and test it in other, in other observables.
Okay.
Okay.
Thank you.
You okay with that? So we have a question from Thomas Schaefer, and he's in another meeting, so he asked me to read the question for you. We tried
Okay.
quark spin depolarization by repeated instanton transitions as a mechanism for small sigma in the old days of the instanton liquid, but couldn't get it to work. Small x physics could be different, of course. Well, it's a comment, I assume.
Yeah. So I missed the first part of what you said.
It's in the chat, but let me read again. We
Yeah, okay.
tried quark spin
Oh.
depolarization by repeated instanton transitions as a mechanism for small sigma in the instanton liquids.
Right. So I actually, in fact, in our paper, we referred to this very nice review by Thomas and Tom Schaefer and Ed Shuriak, where they actually talk about this. And in fact, yeah, so in the instanton liquid model, it looks like you need to induce, stronger interactions between the instantons and anti-instantons to really kind of get this kind of topological screening. So it's very sensitive in that picture to the details of what's going on. But the essence of the ideas, I think, are the same in this. I mean, that's a particular realization of these ideas.
Mm-hmm. Well, I cannot comment on behalf of Thomas to which extent he got the answer, but I think there is at least similarity in the approaches, or at least in the spirit of the physics.
Oh, that's what he says in the chat. Okay, thank you.
Yeah.
I have to look at
okay,
the chat.
I don't see any other questions. Xingang Dong Ji was interested asking some questions and comments, but unfortunately he also excused himself because he had to leave for another meeting. So he said he will approach you directly.
Yeah, so he and I actually have been communicating on these issues. And so I'm sure he and I will have lots of discussions.
So I don't see anybody else in the audience right now wanting to ask the questions. So if there are no more questions, I would like to thank Raju again for a very detailed presentation.